Learning objectives. In this chapter, the user would learn the following in detail. Routing process, types of routing process, static, default, dynamic routing, routing information, protocol RIP, link state routing protocol OSPF, advanced distance vector routing protocol, EIGRP configuration and troubleshooting, device like router and multi-layer switches for routing purpose and configuration command of these devices using their operating system. Advanced distance vector routing protocol. Distance vector protocol. A vector contains both distance and direction, such as RIP, determine the path to remote networks using hop count as the metric. A hop count is defined as the number of times a packet needs to pass through a router to reach a remote destination. Routers using distance vector protocol do not have knowledge of the entire path to a destination. Instead, they use two methods. Number 1. Direction in which router or exit interface a packet should be forwarded. Number 2. Distance from its destination. Distance vector protocols are based on calculating the direction and distance to any link in a network. Direction usually means the next hop address and the exit interface. Distance is a measure of the cost to reach a certain node. The least count route between any two nodes is the route with minimum distance. Each node maintains a vector or a table of minimum distance to every node. The cost of reaching a destination is calculated using various route metrics. RIP uses the hop count of the destination, whereas IGRP takes into account other information such as node delay and available bandwidth. Enhanced Interior Gateway Routing Protocol, or EIGRP, is an advanced distance vector routing protocol that is used on a computer network to help automate routing decisions and configuration. For IP/RIP, the maximum hop is 15. A hop count of 16 indicates an unreachable network. Two versions of RIP exist, version 1 and version 2. IGRP is another example of a distance vector protocol with a higher hop count of 255 hops. A higher hop count allows your network to scale larger. One of the drawbacks of protocols such as RIP and IGRP is convergence time, which is the time it takes for routing information changes to propagate through all your topology. Table describes the characteristics of distance vector protocols. Distance vector protocol summary. Characteristic description. Periodic updates. Periodic updates are sent at a set interval. For IP/RIP, this interval is 30 seconds. Broadcast updates. Updates are sent to the broadcast address 255.255.255.255. Only devices running routing algorithms listen to these updates. Full table updates. When an update is sent, the entire routing table is sent. Triggered updates, also known as flash updates. These are sent when a change occurs outside the update interval. Split horizon. You use this method to stop routing loops. Updates are not sent out an outgoing interface from which the source network was received. This saves on bandwidth as well. Count to infinity. This is the maximum hop count for RIP, it is 15, and for IGRP, it is 255. Algorithm. One algorithm example is Bellman-Ford for RIP. Examples: RIP and IGRP are examples of distance vector protocols. Enhanced Interior Gateway Routing Protocol, or IGRP. Enhanced Interior Gateway Routing Protocol, or IGRP, is an advanced distance vector routing protocol that is used on a computer network to help automate routing decisions and configuration. EIGRP is used on a router to share routes with other routers within the same autonomous system. Unlike other well-known routing protocols such as RIP, EIGRP only sends incremental updates, reducing the workload on the router and the amount of data that needs to be transmitted. The Enhanced Interior Gateway Routing Protocol replaced Interior Gateway Routing Protocol (IGRP) in 1993. One of the major reasons for this was because the design of the Internet protocol had been changed to support classless IPv4 addresses, which IGRP could not support. Almost all routers contain a routing table that contains rules by which traffic is forwarded in a network. If a router does not contain a valid path to the destination, the traffic is discarded. EIGRP is a dynamic routing protocol by which routers automatically share route information. This eases the workload on a network administrator who does not have to configure changes to the routing table manually. In addition to the routing table, EIGRP uses the following tables to store information. Neighbor table. The neighbor table keeps a record of the IP addresses of routers that have a direct physical connection with this router. Routers that are connected to this router indirectly through another router are not recorded in this table as they are not considered neighbors. Topology table. The topology table stores routes that it has learned from neighbor routing tables. Unlike a routing table, the topology table does not store all routes, but only routes that have been determined by EIGRP. The topology table also records the metrics for each of the listed EIGRP routes, the feasible successor and the successors. Routes in the topology table are marked as passive or active. Passive indicates that EIGRP has determined the path for the specific route and has finished processing. Active indicates that EIGRP is still trying to calculate the best path for the specific route. Routes in the topology table are not usable by the router until they are inserted into the routing table. The topology table is never used by the router to forward traffic. Routes in the topology table will not be inserted into the routing table if they are active, are a feasible successor, or a higher administrative distance than an equivalent path. Information in the topology table may be inserted into a router's routing table and can then be used to forward traffic. If the network changes, for example, a physical link fails or is disconnected, the path will become unavailable. EIGRP is designed to detect these changes and will attempt to find a new path to the destination. The old path that is no longer available is removed from the routing table. Unlike most distance vector routing protocols, EIGRP does not transmit all the data in the router's routing table when a change is made, but will only transmit the changes that have been made since the routing table was last updated. EIGRP does not send its routing table periodically, but will only send routing table data when an actual change has occurred. This behavior is more in line with link state routing protocols, thus EIGRP is mostly considered a hybrid protocol. When a router running EIGRP is connected to another router also running EIGRP, information is exchanged between the two routers and a relationship is formed known as an adjacency. The entire routing table is exchanged between both routers at this time. After this has occurred, only differential changes are sent. EIGRP is often considered a hybrid protocol because it also sends link state updates when link states changes. EIGRP provides the following features. Automatic redistribution. IGRP routes can be automatically redistributed into EIGRP and EIGRP routes can be automatically redistributed into IGRP. If desired, you can turn off redistribution. You can also completely turn off EIGRP and IGRP on the router or on individual interfaces. Increased network width. With IP Routing Information Protocol, RIP, the largest possible width of your network is 15 hops. When EIGRP is enabled, the largest possible width is increased to 100 hops and the metric is large enough to support thousands of hops. EIGRP offers the following features. Fast convergence. The dual algorithm allows routing information to converge as quickly as any currently available routing protocols. Partial updates. EIGRP sends incremental updates when the state of a destination changes, instead of sending the entire contents of the routing table. This feature minimizes the bandwidth required for EIGRP packets. Less CPU usage than IGRP. This occurs because full update packets need not be processed each time they are received. Neighbor discovery mechanism. This is a simple hello mechanism used to learn about neighboring routers. It is protocol independent. Variable length subnet masks or VLSMs. Arbitrary route summarization. Scaling. EIGRP scales to large networks. EIGRP has the following four basic components. Neighbor discovery of neighbor recovery. Reliable transport protocol. Dual finite state machine. Protocol dependent modules. Neighbor discovery of neighbor recovery is the process that routers can use dynamically learn of other routers on their directly attached networks. Routers must also discover when the neighbors become unreachable or inoperative. Neighbor discovery of neighbor recovery is achieved with low overhead by periodically sending small hello packets. Once this status is determined, the neighboring routers can exchange routing information. The Reliable Transport Protocol is responsible for guaranteed, ordered delivery of EIGRP packets to all neighbors. It supports intermixed transmission of multicast and unicast packets. Some EIGRP packets must be sent reliably and others need not be. For efficiency, reliability is provided only when necessary. The dual finite state machine embodies the decision process for all route computations. It tracks all routes advertised by all neighbors. Dual uses the distance information known as a metric to select efficient loop-free paths. Dual selects routes to be inserted into a routing table based on feasible successors. A successor is a neighboring router used for packet forwarding that has a least cost path to a destination that is guaranteed not to be a part of a routing loop. When there are no feasible successor but there are neighbors advertising the destination, a recomputation must occur. This is the process whereby a new successor is determined. The protocol-dependent modules are responsible for network layer protocol-specific tasks. An example is the EIGRP module, which is responsible for sending and receiving EIGRP packets that are encapsulated in IP. It is also responsible for passing EIGRP packets and informing dual of the new information received. EIGRP asks dual to make routing decisions, but the results are stored in the IP routing table. Also, EIGRP is responsible for redistributing routes learned by other IP routing protocols. EIGRP configuration and troubleshooting. EIGRP configuration task list. To configure EIGRP, perform the tasks described in the following sections. The tasks in the first section are required. The tasks in the remaining sections are optional. Enabling EIGRP is required. Making the transition from IGRP to EIGRP is optional. Logging EIGRP neighbor agency changes is optional. Configuring the percentage of link bandwidth used is optional. Adjusting the EIGRP metric weights is optional. Applying offsets to routing metrics is optional. Disabling route summarization is optional. Configuring summary aggregate addresses is optional. Configuring floating summary routes is optional. Configuring EIGRP route authentication is optional. Configuring EIGRP protocol independent parameters is optional. Configuring EIGRP subrouting is optional. Monitoring and maintaining EIGRP is optional. Enabling EIGRP. To create an EIGRP routing process, use the following commands beginning in global configuration mode. Step 1. To enable an EIGRP routing process in global configuration mode, gives following command: router config hash router EIGRP autonomous system. Step 2. To associate networks with an EIGRP routing process in router configuration mode, gives following command: router config router hash network number. EIGRP sends updates to the interfaces in the specified networks. If you do not specify the network of an interface, the interface will not be advertised in any EIGRP update, making the transition from IGRP to EIGRP. If we have routers on your network that are configured for IGRP and you want to make a transition to routing EIGRP, we must designate transition routers that have both IGRP and EIGRP configured. In these cases, perform the tasks enabling EIGRP and configuring IGRP in this document. We must use the same autonomous system number in order for routes to be redistributed automatically. Logging EIGRP neighbor agency changes. By default, the system logs EIGRP neighbor agency changes to monitor the stability of the routing system and detect problems. If we disabled logging of such changes and want to re-enable the logging, use the following command in router configuration mode: router config router hash EIGRP log neighbor changes. Enables logging of EIGRP neighbor agency changes. Configuring the percentage of link bandwidth used. By default, EIGRP packets consume a maximum of 50% of the link bandwidth as configured with the bandwidth interface configuration command. To change that value, if a different level of link utilization is required or if the configured bandwidth does not match the actual link bandwidth, it may have been configured to influence route metric calculations. To configure the percentage of bandwidth that may be used by EIGRP on an interface, use the following command in interface configuration mode: router config if hash IP bandwidth percentage EIGRP percentage. Configures the percentage of bandwidth that may be used by EIGRP on an interface. Adjusting the EIGRP metric weights. EIGRP uses the minimum bandwidth on the path to a destination network and the total delay to compute routing metrics. We can use the EIGRP metric weights command to adjust the default behavior of EIGRP routing and metric computations. For example, this adjustment allows us to tune system behavior to allow for satellite transmission. EIGRP metric defaults have been carefully selected to provide optimal performance in most networks. To adjust the EIGRP metric weights, use the following command in router configuration mode: router config router hash metric weights TOS K1, K2, K3, K4, K5. Adjusts the EIGRP metric or K value. EIGRP uses the following formula to determine the total metric of the network. Metric equal to K1 into bandwidth plus K2 into bandwidth divided by 256 minus load plus K3 into delay into K5 divided by reliability plus K4. By default, the EIGRP composite metric is a 32-bit quantity that is a sum of the segment delays and the lowest segment bandwidth that is scaled and inverted for a given route. For a network of homogeneous media, this metric reduces to a hop count. For a network of mixed media, FDDI, Ethernet and serial lines running from 9600 bits per second to T1 rates, the route with the lowest metric reflects the most desirable path to a destination. Applying offsets to routing metrics. An offset list is the mechanism for increasing incoming and outgoing metrics to routes learned via EIGRP. An offset list provides a local mechanism for increasing the value of routing metrics. Optionally, we can limit the offset list with either an access list or an interface. To increase the value of routing metrics, use the following command in router configuration mode. Router config router hash offset list access list number access list name in out offset interface type interface number applies an offset to routing metrics. Disabling route summarization. We can configure EIGRP to perform automatic summarization of subnet routes into network level routes. For example, you can configure subnet 131.108.1.0 to be advertised as 131.108.0.0 over interfaces that have subnets of 192.31.7.0 configured. Automatic summarization is performed when there are two or more network router configuration commands configured for the EIGRP process. By default, this feature is enabled. Disable automatic summarization. Use the following command in router configuration mode. Router config -router hash no auto summary. Disables automatic summarization. Route summarization works in conjunction with the IP summary address EIGRP interface configuration command, in which additional summarization can be performed. If automatic summarization is in effect, there usually is no need to configure network level summaries using the IP summary address EIGRP command. Configuring summary aggregate addresses. We can configure a summary aggregate addresses for a specified interface. If any more specific routes in the routing table, EIGRP will advertise the summary address out the interface with a metric equal to the minimum of all more specific routes. To configure a summary aggregate address, use the following command in interface configuration mode. Router config if hash IP summary address EIGRP autonomous system number IP address mask configures a summary aggregate address. Configuring floating summary routes. We can also use a floating summary route when configuring the IP summary address EIGRP command. The floating summary route is created by applying a default route and administrative distance at the interface level. Configuring EIGRP route authentication. EIGRP route authentication provides Message Digest 5 or MD5 authentication of routing updates from the EIGRP routing protocol. The MD5 keyed digest in each EIGRP packet prevents the introduction of unauthorized or false routing messages from unapproved sources. Before you can enable EIGRP route authentication, we must enable EIGRP. To enable authentication of EIGRP packets, use the following commands beginning in interface configuration mode. Table, first column steps, second column command, and third column purpose. Step 1. Router config hash interface type number. Configure an interface type and enter interface configuration mode. Step 2. Router config if hash IP authentication mode EIGRP autonomous system MD5 enables MD5 authentication in EIGRP packets. Step 3. Under command column, router config if hash IP authentication key chain EIGRP autonomous system key chain under purpose column enables authentication of EIGRP packets. Step 4. Under command column, router config if hash exit router config hash under purpose column exits to global configuration mode. Step 5. Under command column, router config hash key chain name of chain under purpose column identifies a key chain match the name configured in step 1. Step 6. Under command column, router config keychain hash key number. Under purpose column, in keychain configuration mode, identifies the key number. Step 7. Under command column, router config keychain key hash key string text. Under purpose column, in keychain key configuration mode, identifies the key string. Step 8. Under command column, router config keychain key hash accept lifetime start time infinite end time duration seconds. Under purpose column, optionally specifies the time period during which the key can be received. Step 9. Under command column, router config keychain key hash send lifetime start time infinite end time duration seconds. Under purpose column, optionally specifies the time period during which the key can be sent. Each key has its own key identifier specified with the key number keychain configuration command, which is stored locally. The combination of the key identifier and the interface associated with the message uniquely identifies the authentication algorithm and MD5 authentication key in use. We can configure multiple keys with lifetimes. Only one authentication packet is sent regardless of how many valid keys exist. The software examines the key numbers in order from lowest to highest and uses the first valid key it encounters. Note that the router needs to know the time. Configuring EIGRP protocol independent parameters. EIGRP works with AppleTalk IP and IPX. The bulk of this chapter describes EIGRP. However, this section describes EIGRP features that work for AppleTalk IP and IPX. To configure such protocol independent parameters, perform one or more of the tasks in the following sections. Adjusting the interval between hello packets and the hold time. Disabling split horizon. Adjusting the interval between hello packets and the hold time. You can adjust the interval between hello packets and the hold time. Routing devices periodically send hello packets to each other to dynamically learn of other routers on their directly attached network. This information is used to discover neighbors and to learn when neighbors become unreachable or inoperative. By default, hello packets are sent every 5 seconds. The exception is on low-speed, non-broadcast multi-access NMA media, where the default hello interval is 60 seconds. We can configure the hold time on a specified interface for a particular EIGRP routing process designated by the autonomous system number. The hold time is advertised in hello packets and indicates to neighbors the length of time they should consider the sender valid. The default hold time is 3 times the hello interval, or 15 seconds. For slow-speed NMA networks, the default hold time is 180 seconds. To change the interval between hello packets, use the following command in interface configuration mode. Router config if hash IP hello interval EIGRP autonomous system number seconds. Configures the hello interval for an EIGRP routing process. On very congested and large networks, the default hold time might not be sufficient time for all routers to receive hello packets from their neighbors. In this case, we may want to increase the hold time. To change the hold time, use the following command in interface configuration mode. Router config if hash IP hold time EIGRP autonomous system number seconds. Configures the hold time for an EIGRP routing process. Disabling split horizon. Split horizon controls the sending of EIGRP update and query packets. When split horizon is enabled on an interface, update and query packets are not sent for destinations for which this interface is the next hop. Controlling update and query packets in this manner reduces the possibility of routing loops. By default, split horizon is enabled on all interfaces. Split horizon blocks route information from being advertised by a router out of any interface from which that information originated. This behavior usually optimizes communications among multiple routing devices, particularly when links are broken. However, with non-broadcast networks such as frame relay and SMDS, situations can arise from which this behavior is less than ideal. For these situations, including networks in which you have EIGRP configured, you may want to disable split horizon. To disable split horizon, use the following command in interface configuration mode. Router config if #no IP split horizon EIGRP autonomous system number. Configuring EIGRP stub routing. The EIGRP stub routing feature improves network stability, reduces resource utilization, and simplifies stub router configuration. Stub routing is commonly used in hub and spoke network topology. In hub and spoke network, one or more end stub networks are connected to a remote router, the spoke that is connected to one or more distribution routers, or the hub. The remote router is adjacent only to one or more distribution routers. The only route for IP traffic to follow into the remote router is through a distribution router. This type of configuration is commonly used in WAN topologies where the distribution router is directly connected to a WAN. The distribution router can be connected to many more remote routers. Often, the distribution router will be connected to 100 or more remote routers. In a hub and spoke topology, the remote router must forward all non-local traffic to a distribution router, so it becomes unnecessary for the remote router to hold a complete routing table. Generally, the distribution router need not send anything more than a default route to the remote router. When using the EIGRP stub routing feature, we need to configure the distribution and remote routers to use EIGRP and to configure only the remote router as a stub. Only specified routes are propagated from the remote or stub router. The stub router responds to all queries for summaries, connected routes, redistributed static routes, external routes, and internal routes with the message inaccessible. A router that is configured as a stub will send a special peer information packet to all neighboring routers to report its status as a stub router. Any neighbor that receives a packet informing it of a stub status will not query the stub router for any routes, and a router that has a stub peer will not query that peer. The stub router will depend on a distribution router to send the proper updates to all peers. EIGRP stub routing configuration task list. To configure EIGRP stub routing, perform the tasks described in the following sections. The tasks in the first section are required. The task in the last section is optional. Configuring EIGRP stub routing is required. Verifying EIGRP stub routing is optional. Configuring EIGRP stub routing. To configure a remote or spoke router for EIGRP stub routing, use the following commands beginning in router configuration mode. Table, first column steps, second column command, and third column purpose. Step 1. Under command column, router config #router EIGRP 1 under purpose column configures a remote or distribution router to run an EIGRP process. Step 2. Under command column, router config router #network number under purpose column associates networks with an EIGRP routing process in router configuration mode. Step 3. Under command column, router config router #EIGRP stub receive only connected static summary under purpose column configures a remote router as an EIGRP stub router. Verifying EIGRP stub routing. To verify that a remote router has been configured as a stub router with EIGRP, use the show IP EIGRP neighbor detail command from the distribution router in privileged EXEC mode. The last line of the output will show the stub status of the remote or spoke router. The following example shows output is from the show IP EIGRP neighbor detail command. Router hash show IP EIGRP neighbor detail. IP EIGRP neighbors for process 1. H address interface hold uptime SRTT RTO Q SEQ type SEC MS CNT NUM 0 10.1.1.2 SE3 /1 11 00 00 59 1 4500 07 version 12.1 /1.2 retrans 2 retrice 0 stub peer advertising connected summary routes. Monitoring and maintaining EIGRP. To delete neighbors from the neighbor table, use the following command in EXEC mode. Router hash clear IP EIGRP neighbors IP address interface type. To display various routing statistics, use the following commands in EXEC mode as needed. Table first column command, second column purpose. Router hash show IP EIGRP interfaces interface type. Interface number as number displays information about interfaces configured for EIGRP. Under command column, router hash show IP EIGRP neighbors interface type as number static under purpose column displays the EIGRP discovered neighbors. Under command column, router hash show IP EIGRP topology as number IP address mask under purpose column displays the EIGRP topology table for a given process. Under command column, router hash show IP EIGRP traffic as number under purpose column displays the number of packets sent and received for all or a specified EIGRP process. To enable EIGRP stub routing packet debugging, use the following command in privileged EXEC mode. Router hash debug EIGRP packet stub displays debug information about the stub status of peer routers. Main troubleshooting flowchart. In order to troubleshoot EIGRP, use this flowchart starting at the box marked main. Depending on the symptoms, the flowchart might refer to one of the three flowcharts. Main troubleshooting flowchart as shown here. Neighbor check. Neighbor check as shown here. If you are not able to ping successfully between neighbors, run the debug IP packet command in order to verify if the hellos are sent to multicast address 224.0.0.10. Number 1. Issue the show IP EIGRP interface command to verify. Number 2. Issue the show interface serial command to verify. If the interface is not listed, ensure it is not a passive interface. If passive interface default is enabled, then the interface needs to be manually removed from the passive interface list with the no passive interface command. Neighbor check as shown here. If you experience the problems with EIGRP flapping across the GRE interface tunnel, it is possible that you have to configure the keep alive 10.3 and IP TCP adjust MSS 1400 commands at both ends of the GRE tunnel. 3. Issue the show IP interface command to verify. Redistribution check. Number 4. Issue the show IP EIGRP topology net mask command to verify. Redistribution check as shown here. Route check. Number 5. Issue the show IP route EIGRP command to verify. Route check as shown here. Number 6. Issue the show IP EIGRP topology command to verify. If routes are not seen in the topology table, issue the clear IP EIGRP topology command. Route check as shown here. Link State Routing Protocol (OSPF). Link state routing protocols are one of the two main classes of routing protocols used in packet switching networks for computer communications, the other being distance vector routing protocols. Examples of link state routing protocols include Open Shortest Path First or OSPF and Intermediate System to Intermediate System (IS to IS). The link state protocol is performed by every switching node in the network, that is, nodes that are prepared for forward packets in the internet. These are called routers. The basic concept of link state routing is that every node constructs a map of connectivity to the network in the form of a graph showing which nodes are connected to which other nodes. Each node then independently calculates the next best logical path from it to every possible destination in the network. The collection of best paths will then form the node's routing table. This contrasts with the distance vector routing protocols, which work by having each node share its routing table with its neighbors. In a link state protocol, the only information passed between nodes is connectivity related. The OSPF or Open Shortest Path First protocol is one of a family of IP routing protocols and is an interior gateway protocol or IGP for the internet used to distribute IP routing information throughout a single autonomous system or AS in an IP network. The OSPF protocol is a link state routing protocol, which means that the routers exchange topology information with their nearest neighbors. The topology information is flooded throughout the AS so that every router within the AS has a complete picture of the topology of the AS. This picture is then used to calculate end-to-end paths through the AS, normally using a variant of the Dijkstra algorithm. Therefore, in a link state routing protocol, the next hop address to which data is forwarded is determined by choosing the best end-to-end path to the eventual destination. The main advantage of a link state routing protocol like OSPF is that the complete knowledge of topology allows routers to calculate routes that satisfy particular criteria. This can be useful for traffic engineering purposes where routes can be constrained to meet particular quality of service requirements. The main disadvantage of a link state routing protocol is that it does not scale well as more routers are added to the routing domain. Increasing the number of routers increases size and frequency of the topology updates and also the length of time it takes to calculate end-to-end routes. This lack of scalability means that a link state routing protocol is unsuitable for routing across the internet at large, which is the reason why IGPs only route traffic within a single AS. In practice, there are a number of optimizations which are used. Most importantly, whenever a change in the connectivity map happens, it is necessary to recompute the shortest path tree and then recreate the routing table. Also, the routing table would normally be filled in as the shortest path tree is computed, instead of making it a separate operation. The optimized link state routing protocol for mobile ad hoc networks. The optimized link state routing protocol (OLSR) is a link state routing protocol optimized for mobile ad hoc networks, which can also be used on other wireless ad hoc networks. OLSR is proactive. It uses hello and topology control, that is TC, messages to discover and disseminate link state information into the mobile ad hoc network. Using hello messages, each node discovers two hop neighbor information and elects a set of multi-point relays, that is MPRs. MPRs makes OLSR unique from other link state routing protocols. Individual nodes use the topology information to compute next hop paths regard to all nodes in the network utilizing shortest hop forwarding paths. Device like router and multi-layer switches for routing purpose and configuration command of these devices using their operating system. Router. A router is a device that forwards data packets along networks. A router is connected to at least two networks, commonly two LANs or WANs, or a LAN and its ISP's network. Routers are located at gateways, the places where two or more networks connect. A router is a networking device that forwards data packets between computer networks. Routers perform the traffic directing functions on the internet. A data packet is typically forwarded from one router to another through the networks that constitute the internet work until it reaches its destination node. A router is connected to two or more data lines from different networks, as opposed to a network switch which connects data lines from one single network. When a data packet comes in on one of the lines, the router reads the address information in the packet to determine its ultimate destination. Then, using information in its routing table or routing policy, it directs the packet to the next network in its journey. This creates an overlay internetwork. The most familiar type of routers are home and small office routers that simply pass data, such as web pages, email, IM, and videos between the home computers and the internet. An example of a router would be the owner's cable or DSL router, which connects to the internet through an ISP. More sophisticated routers, such as enterprise routers, connect large business or ISP networks up to the powerful core routers that forward data at high speed along the optical fiber lines of the internet backbone. Though routers are typically dedicated hardware devices, use of software-based routers has grown increasingly common. Routers may also be used to connect two or more logical groups of computer devices known as subnets, each with a different subnetwork address. The subnet addresses recorded in the router do not necessarily map directly to the physical interface connections. A router has two stages of operation called planes. Number 1. Control plane. A router maintains a routing table that lists which route should be used to forward a data packet and through which physical interface connection. Static and dynamic routes are stored in the routing information base RIB. The control plane logic then strips the RIB from non-essential directives and builds a forwarding information base or FIB to be used by the forwarding plane. Number 2. Forwarding plane. The router forwards data packets between incoming and outgoing interface connections. It routes them to the correct network type using information that the packet header contains. It uses data recorded in routing table control plane. Overview of router configuration. Once we log in into a router, you instantly enter the so-called user mode. The prompt router name appears. From this mode, you can only see some statistic information. To view and change the configuration of the router, you have to enter into the privileged mode by entering the enable command by following the steps. Router A greater than enable router A hash. To be able to make global changes to the configuration of the router, you have to enter the global configuration mode. Once we achieve that, we are able to access any possible subsequent configuration mode and make global changes. Router A hash configure terminal or config T for short. Router A config hash. Now we have the control of our device. If we need to modify our router's configuration, then you enter the appropriate configuration mode. For example, if you want to make a change to our fast Ethernet interface 0/0, then we have to enter interface configuration mode and make our modifications from there. Here are the steps. Router A config hash interface fast Ethernet 0/0. Router A config if hash. Prompt router A config if hash indicates we are in interface configuration mode. At any time and any mode we are in, we can insert a question mark and the router will automatically show all the possible commands or option parameters we can apply at that specific time. Router A config if hash question mark. Interface configuration commands. Access expression. Build a bridge Boolean access expression. ARP set, ARP type, ARPA, probe, snap, or timeout. Backup modify, backup parameters. IP interface, Internet Protocol config commands. List of the most important configuration modes along with the commands used to enter these modes. Name our router and adjust its clock. To apply an identifier to our router, use the hostname command. To adjust the clock on the router, use the clock set command. Always use the to help us correctly finish the command. Router config hash hostname router A config hash exit router A hash clock set HHMMSS current time router A hash clock set 0930000131 day of the month router A hash clock set 09300018 month of the year router A hash clock set 09300018 November 1993 2035 year router A hash clock set 09300018 November 2007 Setting banners. It's a good idea to configure security notices to be displayed every time someone accesses our router. These notices are considered to be valid legal notices. The most useful banner is the so-called Message of the Day or MOTD banner. This banner is displayed to every user connecting to the router either via telnet, console port or auxiliary port. This is how we can set it on our router. Router A config hash banner MOTD ? Line C banner text C where C is a delimiting character. Router A open bracket config close bracket hash banner MOTD hash asterisk 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 authorized users only asterisk 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 hash. Setting passwords. The first thing we need to set on your router before you even modify its configuration is the secret password which is used to secure privileged mode access to the router. This password uses strong encryption algorithms making it impossible to break. It should really be our number one priority to make sure we have set this password on your router. Use the enable secret commands to apply it to our router. Router A config hash enable secret test. For added security, we can apply user mode passwords. When users access the router either remotely via telnet or via the console terminal, then this kind of passwords prompts the users for authentication. To set this password for users accessing the router remotely via telnet, use the line VTY first line number, last line number command. The necessary steps to configure this are the following. Router A config hash line VTY04. Router A config line hash login. Router A config line hash password testing. To set user mode password for the console line, perform the following. Router A config hash line console 0. Router A config line hash login. Router A config line hash password testing. A couple of important commands we can use at the line configuration mode are the exec timeout minutes, seconds and logging synchronous commands. The first one sets the timeout for the specific line and the second one stops annoying pop-up messages from disrupting whatever we are trying to type. Here is an example of how to apply these commands. Router A config hash line console 0. Router A config line hash exec timeout 10 0. Router A config line hash logging synchronous. Managing router interfaces. At the interface configuration mode, we can apply an IP address and subnet mask to an interface using the IP address command. We can also shut down or activate an interface by using the shutdown or no shutdown commands respectively. These two commands are very basic and we will definitely use them all the time. Here is an example. Router A config hash interface fast Ethernet 0/0. Router A config if hash IP address 192.168.10.1 255.255.255.0. Router A config if hash no shutdown. It is a good idea to apply descriptions to our connected interfaces as well. This will be very helpful, especially when we are troubleshooting things. Simply use the description command like this: Router A config hash interface fast Ethernet 0/0. Router A config hash description connection to central switch. Displaying and verifying things. There is one privileged mode command that we will find ourselves using extensively, the show command, which has a broad usage including viewing routers configuration, verifying interfaces configuration, viewing interfaces status. Here are a few important show commands we will find helpful to use. Router A hash show running configuration, Router A hash show clock, Router A hash show interfaces, Router A hash show IP interfaces brief, Router A hash show interfaces description. Multi-layer switch. Multi-layer switches have higher latency of layer 3 routing. Spanning tree must be disabled in order to implement routing on a multi-layer switch. Multi-layer switches are more expensive than router on a stick implementations. Multi-layer switches are limited to using trunk links for layer 3 routing. Prerequisites. The following prerequisites are necessary before MLS can function. A VLAN interface must be configured on both the switch and the router. For information on configuring inter-VLAN routing on the RSM or an external router, IP multicast MLS must be configured on the switch. IP multicast routing and PIM must be enabled on the router. Restrictions. We must also configure the Catalyst 5000 series switch in order for IP multicast MLS to function on the router. The restrictions in the following sections apply to IP multicast MLS on the router. Router configuration restrictions, external router guidelines, access list restrictions and guidelines. Router configuration restrictions. IP multicast MLS does not work on internal or external routers in the following situations. Number 1. If IP multicast MLS is disabled on the RPF interface for the flow using the no MLS RP IP multicast interface configuration command. Number 2. For IP multicast groups that fall into these ranges where asterisk is in the range from 0 to 255 -224.0.0. asterisk through 239.0.0. asterisk -224.128.0. asterisk through 239.128.0. asterisk. Number 3. For PIM auto RP multicast groups, IP multicast group addresses 224.0.1.39 and 224.0.1.40. Number 4. For flows that are forwarded on the multicast shared tree, that is *G forwarding when the interface or group is running PIM spas mode. Number 5. If the shortest path tree or SPT bit for the flow is cleared when running PIM spas mode for the interface or group. Number 6. When an input rate limit is applied on an RPF interface. Number 7. For any RPF interface with access lists applied. Number 8. For any RPF interface with multicast boundary configured. Number 9. For packets that require fragmentation and packets with IP options. However, packets in the flow that are not fragmented or that do not specify IP options are multi-layer switched. Number 10. On external routers, for source traffic received at the router on non-ISL or non-802.1q interfaces. Number 11. For source traffic received on tunnel interfaces such as M-bone traffic. Number 12. For any RPF interface with multicast tag switching enabled. External router guidelines. Follow these guidelines when using an external router. The connection to the external router must be over a single ISL or 802.1q trunk link with sub-interfaces using appropriate encapsulation type configured. A single external router can serve as the MMLS RP for multiple switches, provided each switch connects to the router through a separate ISL or 802.1q trunk link. If the switch connects to a single router through multiple trunk links, IP multicast MLS is supported on one of the links only. We must disable IP multicast MLS on the redundant links using the no MLS RP IP multicast interface configuration command. We can connect end hosts, source or multicast destination devices through any media like Ethernet, Fast Ethernet, ATM and FDDI. But the connection between external routers and the switch must be through Fast Ethernet or Gigabit Ethernet interfaces. Access list restrictions and guidelines. The following restrictions apply when using access lists on interfaces participating in IP multicast MLS. All standard access lists are supported on any interface. The flow is multi-layer switched on all interfaces on which the traffic for the flow is allowed by the access list. Layer 4 port-based extended IP input access lists are not supported. For interfaces with these access lists applied, no flows are multi-layer switched. Extended access lists on the RPF interface that specify conditions other than Layer 3 source, Layer 3 destination, and IP protocol are not multi-layered switched. Configuring and monitoring IP multicast MLS. To configure your Cisco router for IP multicast MLS, perform the tasks described in the following sections. The first two sections contain required tasks, the remaining tasks are optional. To ensure a successful multicast MLS configuration, we must also configure the catalyst switches in your network. Number 1. Enabling IP multicast routing, that is required. Number 2. Enabling IP PIM, that is required. Number 3. Enabling IP multicast MLS, that is optional. This is a required task if you disabled it. Number 4. Specifying a management interface, that is optional. Number 1. Enabling IP multicast routing. We must enable IP multicast routing globally on the MMLS RPs before we can enable IP multicast MLS on router interfaces. To enable IP multicast routing on the router, use the following command in router configuration mode. Router config #IP multicast routing enables IP multicast routing globally. Number 2. Enabling IP PIM. We must enable PIM on the router interfaces connected to the switch before IP multicast MLS will function on those router interfaces. To do so, use the following commands beginning in interface configuration mode. Step 1. Router config #interface type number configures an interface. Step 2. Router config if #IP PIM open curly bracket dense mode vertical bar space mode vertical bar space dense mode closed curly bracket enables PIM on the interface. Number 3. Enabling IP multicast MLS. IP multicast MLS is enabled by default when you enable PIM on the interface. Perform this task only if you disabled IP multicast MLS and you want to re-enable it. To enable IP multicast MLS on an interface, use the following command in interface configuration mode. Router config if #MLS RP IP multicast enables IP multicast MLS on an interface. Number 4. Specifying a management interface. When we enable IP multicast MLS, the sub-interface or VLAN interface that has the lowest VLAN ID and is active in the up state is automatically selected as the management interface. The one-hop protocol multi-layer switching protocol MLSP is used between a router and a switch to pass messages about hardware switched flows. MLSP packets are sent and received on the management interface. Typically, the interface in VLAN 1 is chosen if that interface exists. Only one management interface is allowed on a single trunk link. In most cases, we recommend that the management interface be determined by default. However, we can optionally specify a different router interface or sub-interface as the management interface. We recommend using a sub-interface with minimal data traffic so that multicast MLSP packets can be sent and received more quickly. If the user configured management interface goes down, the router uses the default interface, the active interface with the lowest VLAN ID, until the user configured interface comes up again. To change the default IP multicast MLS management interface, use the following command in interface configuration mode. Router config if #MLS RP IP multicast management interface configures an interface as the IP multicast MLS management interface. Monitoring and maintaining IP multicast MLS. To monitor and maintain an IP multicast MLS network, use the following commands in exec modes as needed. Router #show IP mroute group name vertical bar group address source displays hardware switching state for outgoing interfaces. Router #show IP PIM interface type number count displays PIM interface information. Router #show MLS RP IP multicast locate group source VLAN ID vertical bar statistics vertical bar summary displays layer 3 switching information. Routing Information Protocol or RIP. RIP is a standardized distance vector protocol designed for use on smaller networks. RIP was one of the first two distance vector routing protocols and is supported on a wide variety of systems. RIP adheres to the following distance vector characteristics. RIP sends out periodic routing updates every 30 seconds. RIP sends out the full routing table every periodic update. RIP uses a form of distance as its metric, in this case hop count. RIP uses the Bellman forward distance vector algorithm to determine the best path to a particular destination. Other characteristics of RIP include RIP supports IP and IPX routing. RIP utilizes UDP port 520. RIP routes have an administrative distance of 120. RIP has a maximum hop count of 15 hops. Any network that is 16 hops away or more is considered unreachable to RIP. Thus, the maximum diameter of the network is 15 hops. A metric of 16 hops in RIP is considered a poison route or infinity metric. If multiple paths exist to a particular destination, RIP will load balance between those paths by default up to 4 only if the metric or hop count is equal. RIP uses a round-robin system of load balancing between equal metric routes, which can lead to pinhole congestion. For example, two paths might exist to a particular destination, one going through a 9600 baud link, the other via a T1. If the metric or hop count is equal, RIP will load balance, sending an equal amount of traffic down the 9600 baud link and the T1. This will obviously cause the slower link to become congested. Routing process. Routing is the process of selecting best paths in a network. In the past, the term routing also meant forwarding network traffic among networks. Routing is performed for many kinds of networks, including the telephone network like circuit switching, electronic data networks such as internet, and transportation networks. The routing process usually directs forwarding on the basis of routing tables, which maintain a record of the routes to various network destinations. Thus, constructing routing tables which are held in the router's memory is very important for efficient routing. Most routing algorithms use only one network path at a time. Multipath routing techniques enable the use of multiple alternative paths. The following elements to decide which routes to install into the routing table sorted by priority. Number 1. Prefix length, where longer subnet masks are preferred independent of whether it is within a routing protocol or over different routing protocol. Number 2. Metric, where a lower metric or cost is preferred, only valid within one and the same routing protocol. Number 3. Administrative distance, where a route learned from a more reliable routing protocol is preferred, only valid between different routing protocols. Types of routing process. Number 1. Static routing. This is the method by which an administrator manually adds routes to the routing table of a router. This is a method for small networks, but it is not scalable for larger networks. Number 2. Default routing. This is the method where all routers are configured to send all packets towards a single router. This is a very useful method for small networks or for networks with a single entry and exit point. It is usually used in addition to static and or dynamic routing. Number 3. Dynamic routing. It is the method where protocols and algorithms are used to automatically propagate routing information. This is the most common method and most complex method of routing. Static. Static routing. A static route is a route that is manually configured on the router. Simply we can say a static route is a route that is created manually by a network administrator. The information about the networks that are directly connected to the active router interface is added to the routing table initially, and they are known as connected routes. The second way that the router can learn static routes are by configuring the routes manually. When you manually add routes to the routing table, it is called static routing. There are advantages and disadvantages in using static routing. The advantages are: Number 1. There is no overhead in terms of CPU usage of the router as well as bandwidth between routers. When dynamic routing is used, packets are exchanged between routers and that uses bandwidth. That can be costly when they traverse across WAN links. The routers also need to process these packets, and that consumes some CPU cycles as well. Number 2. It adds a certain degree of security since the administrator controls which routes the routers can know and learn. The disadvantages of static routing are: Number 1. The administrator needs to know the internet work so well that he or she knows where each destination network lies and which is the next hop towards it. Number 2. Every change needs to be manually done on each router in the internet work. Number 3. In large networks, this can be unmanageable. Default. Default routing. Default routing can be considered a special type of static routing. The difference between a normal static route and a default route is that a default route is used to send packets destined to any unknown destination to a single next hop address. Without any static routes, it receives a packet destined to 192.168.5.0/24. It will drop it since it does not know where the destination network is. If a default route is added in router 1 with next hop address of router 2, all packets destined to any unknown destination such as 192.168.5.0/24 will be sent to router 2. Default routes are useful when dealing with a network's single exit point. It is also used when a bulk of destination networks have to be routed to a single next hop device. When adding a default route, you should ensure that the next hop device can route the packet further, or else the next hop device will drop the packet. Another point to remember is that when a more specific route to a destination exists in the routing table, the router will use that route and not the default route. The only time the router will use the default route is when a specific route does not exist. Dynamic routing. Dynamic routes are routes that a router learns by using a routing protocol. Routing protocols will learn about routes from other neighboring routers running the same routing protocol. Dynamic routing protocols share network numbers a router knows about and how to reach these networks. Using a routing protocol is easier than static routing and default routing, but it is more expensive in terms of CPU and bandwidth usage. Every routing protocol defines its own rules for communication between routers and selecting the best route. Routing protocols are broadly classified as interior gateway protocols or IGP or exterior gateway protocols EGP. IGPs are used to exchange routing information within Internet networks that fall under a single administrative domain, also called autonomous systems. EGPs, on the other hand, are used to exchange routing information between different autonomous systems. Common examples of IGPs are Routing Information Protocol, that is RIP, Enhanced Interior Gateway Routing Protocol or EIGRP, and Open Shortest Path First, that is OSPF. Conclusion. In this chapter, we have covered the following in detail: routing process, types of routing process, static, default, dynamic routing, routing information, protocol RIP, link state routing protocol OSPF, advanced distance vector routing protocol, EIGRP configuration and troubleshooting, device like router and multi-layer switches for routing purpose and configuration command of these devices using their operating system.